perfect. Okay, give me a second. Yes, all right. My name is Trygve Svalheim, and I am a PhD student at the University of Oslo. So I'll be presenting today the component separation results from the BeyondPlanck channel, the project, and our plans for the expansion into Cosmoglobe. So by now you're probably all familiar with this figure right here. And this shows the end-to-end analysis loop we developed through the BeyondPlanck project. So this shows the raw satellite time streams to calibration and into map making and component separation and power spectra, and lastly into parameter estimation. And this then is used to inform the next iteration of the full Bayesian loop. So the topic of this presentation in particular is this part down on the lower right-hand side, the component separation and what we have so far here. Okay, so a more mathematical representation of the analysis, which Matthew already showed, is you can see here. And in our analysis, we have billions of free parameters that we wish to sample for the full system. And sampling directly from the posterior distribution is simply impossible. So that's why we resort to the Gibbs sampling procedure that Matthew already talked to you about. And this is where we iteratively sample one part of the system where we're keeping the other parameters fixed. So after we repeat this for more than 1,000 samples, we get a completely unique representation of the full posterior and the interplay between the foregrounds and the systematics. So what I will talk about here is these 2 points here, the 5th and the 6th point, which is the component amplitudes and spectral parameters. So the included data in the BeyondPlanck analysis has been carefully selected to complement the focus of the analysis, and that is the LFI time order data. So that's why the included bands are, of course, the LFI time order data, and also the Planck 353 channel up on the high frequencies here, and that's for polarization, and for temperature intensity analysis, we use the 857 band to constrain the thermal dust component, the red line here. So in addition to this, we also included WMAP KA to V band for better low frequency constraint. And in intensity, we also included Haslam at 408 megahertz for synchrotron constraint in intensity. So in addition to this, we also actually include full covariance matrices in WMAP for polarization. And this drastically improves our ability to identify noise on a band-to-band basis. And this really mitigates the systematic effect leakage from one band to another, so that the WMAP systematics are contained to those residual maps and whatnot. So we also note here, and a very important thing that I will be stressing throughout this presentation is that this is a sparse data set. So this is first and foremost what we did here is a showcase of the algorithm, and we're not aiming for state-of-the-art constraints, but rather show what we have the potential to do and what we can do together. And because of this, for the BeyondPlanck analysis, we added regularization noise to the WMAP bands and also omitted the K band as well as the W band. And of course, you'll notice there's no intermediate Planck bands here. So, yeah. And before we continue, I want to present the sky as we interpret it in BeyondPlanck, and the level of complexity that the included data allows for currently. So the components in our model are, of course, the CMB, which is represented by a black body, and the relativistic quadrupole term here, the other A that's not marked. That's fixed, that's not sampled in our framework. And the synchrotron component modeled by a power law with an amplitude and a power law index. The free, which is only sampled in intensity, hence the thinner font here. And here it also has the amplitude, but a fixed electron temperature, which we will come back to. And we have a spinning dust or AME component, which uses a peak shifted SP dust 2 model with an amplitude and a new peak. Thermal dust modeled with a modified black body with a free amplitude and a beta and a frozen temperature term, and also the point sources here. And also for this analysis, we're not sampling any Sunyaev-Salvage effect, zodiac light, or CIB, and that's all for the future. But for this analysis, all spectral parameters apart from one is sampled as one single full sky value using relatively rudimentary models. So this is, of course, far from ideal. And this is, like I said previously, a consequence of a small data set. And this underscores the importance of the potential collaboration through Cosmoglobe and how including contributions and collaborating can greatly improve our ability to constrain the sky. So, yeah, for example, here, these parameters are not being sampled right now. That's because of the red ones, and also these models can be made a lot more detailed and complex in a system where we have more input data. So in the BeyondPlanck analysis, there were several other things that we did to kind of combat this or work around this issue of having a small data set. And one of these things is including amplitudes priors in intensity. And this is because we have to mitigate degeneracies between CMB, free, and AME without including too much bias. So the plots on the right here show a 20 by 20 degree area around the galactic south pole, where we reduce the CMB leakage into the amplitude components of the AME on the left and the free on the right by applying priors in ALM space. So again, this is a measure necessary because of the low constraining power. But it seems to work, and we do actually reduce some of the amplitude here. And another one of the adjustments that we make, or another one of the angles that we use in the BeyondPlanck project is the inclusion of spectral variation sampling in synchrotron. And this is to investigate any potential spatial variations across the sky in synchrotron. So here we divide the sky into 4 separate regions, and to see any the broad strokes of any spectral index spatial variations. And of course, this ideally would be done on a pixel by pixel basis, so that the resulting map is a full pixelized representations of the synchrotron beta variations. But that's for the future. So for the results, to assess the goodness of fit of our first, our final sampled model, we look at the residual maps, and this is after we remove the sample model, and we can see that mostly noise remains, and this is all in polarization. So there's only small or a few obvious large-scale systematic effects or foreground morphology left, and it seems that we're doing a good job at fitting our model. And while these residuals do look promising, any additional cross checks would of course be ideal, as we don't expect any, or our rudimentary model to be a perfect fit in any way. So seeing how several of these frequencies serve as a reference for the sky components, for example, the 30 here, the 70 and the 353, all serve as reference bands for different sky components. They'll have less signal in the residuals automatically as an effect of the way we do this. That's why we see some extra residual in the 44 gigahertz band, and that might be a good thing, because we get this cross check. So here we show the intensity amplitude maps, where we have separately modeled AME, amplitude, free synchrotron, and dust. In polarization, we see the same thing for the thermal dust and the synchrotron component, but here as an animation, I don't know if you can see it actually moving properly here, but it's 200 samples of a total of 1200. So we can see how the system fluctuates as we move over Gibbs iterations. And we see mainly these noise fluctuations, and in the first few tenths of samples, we can actually see the burn-in of the synchrotron amplitude on the lower right here. So we see that it stabilizes and moving towards convergence. And the dust here is also quite stable, and that shows mostly realizations of white noise, because it's more or less set by the 353 gigahertz channel. But if we were to include more high-frequency data sets, for example, the existing HFI or any collaboration through this project, we would start to see things happen here as well. So moving on to this plot, and this is perhaps the most important representation of the full end-to-end analysis in terms of the component separation. So these are histograms that show the distribution of sampled values for the synchrotron beta component in the spur region. If you remember where we divided the sky into these 4 regions, and the spur region was one of those regions. So here the dashed lines show 2 separate runs with a stationary set of instrumental parameters. And the dotted lines are the priors that we apply to each of the colored runs. And the solid line here shows the full BeyondPlanck analysis, where we marginalize over all the TOD parameters. And the takeaway here is that given a set of instrumental parameters, we get a wildly different result than if we explore the full space of possibilities. And the red line shows that even if we drastically change the prior, we're still data-driven enough in our analysis to end up with the reasonable values. So even though the solid distribution is wider, it's a much more realistic result and shows the true benefit of a joint analysis. So these plots show the foreground overview of the CMB frequency domain as derived by the BeyondPlanck project. Mostly, and current constraints we have put on those components. And as mentioned several times already, the BeyondPlanck data alone cannot provide any state-of-the-art results. So the conclusion here is that we have provided a framework for future end-to-end analysis that can greatly benefit from a community working together with this. So if any of what I've talked to here intrigued you, don't forget to join the Thursday session, where we talk about how we can model the microwave sky in the future. So with your involvement now, we can continue what we started with in BeyondPlanck and create a global cosmological analysis. So, any questions? And thank you to our sponsors.